Hello everyone, welcome to my presentation. Today I'm excited to present our work of an evaluation of the strategies to improve continuous integration. Continuous integration is a popular practice in modern software engineering that encourages developers to check in their code, build and test their software in frequent intervals. CI benefits the developing process because bugs are detected early and are easy to track down due to small change sets. Unfortunately, as many developers work on many projects and they all build and test their code frequently, CI becomes a high-cost process. Google estimates the cost of running a CI system in millions of dollars, and developers have to wait for more than 30 minutes to receive the test results. CI is expensive because there is a high workload that increases the computational cost in the system and may delay the feedback time as well. As a result, two important problems arise due to high workloads. The first problem is the large computational effort, and the second problem is a long time to feedback. There are many existing research aiming to address this problem. Let me use timelines to explain how they work. In our example timeline, each build includes build preparation and test phases. We use red rectangles to represent failing tests and green rectangles to represent passing tests. First, some existing approaches target saving the CI computational cost by selectively executing failing builds or tests and save the cost of executing passing ones. In other words, they aim to only observe failures because failures are considered to be more valuable by providing actionable feedback. These approaches can be executed on two levels, build level and test level. Build selection approaches skip builds fully, including all build and test phases, such as build 2 and 3. Here we use dashed rectangles with lead shade to represent skipped executions. Test selection approaches only skip tests in one build. Other parts are executed as normal. However, there are two common mistakes for selection approaches caused by mispredictions on passing executions and missing predictions on failing executions. The former pulls down the cost-saving ability, while the latter results in skipping those failing executions and missing the observation of failures. Second, other prior work have a different goal to advance the time to feedback by prioritizing builds or tests to make sure failing ones happen in an earlier time. They achieved this goal by predicting which execution is going to fail and execute them first. This prioritization process can also happen on both build and test granularity. Build prioritization approaches aim to prioritize builds that are waiting for executions to make sure failing builds get observed first. Test prioritization approaches target prioritizing tests within a build so that test failures can be found earlier. However, though prioritization approaches can advance time to feedback, but it cannot save any computational cost. All these approaches can be used to improve CI and they all have their own strengths. However, they were proposed and evaluated under different settings, making it hard to compare them. As a result, in this work, we want to evaluate them in the same experimental settings. Our work is based on a popular dataset, Travis Torrent. To be able to replicate existing approaches, we also extended Travis Torrent to have more information such as test and change file information. We include all selection and prioritization techniques in build and test granularities that are designed for CI. Since the field of test selection is older than CI, we also search the literature and try to include the state-of-art techniques before CI becomes popular. Therefore, we totally include 3 build selection approaches, 3 test selection approaches, 1 build prioritization technique, and 3 test prioritization techniques. To evaluate the strengths and weaknesses of these approaches in a comprehensive way, we included metrics of 3 dimensions. First, We use a matrix of computational cost reduction dimension to understand this approach's ability of cost saving. For example, we measure the build time saved as a proportion of escaped build duration among all build time. Second, since mispredictions on failures by these approaches can result in falsely escaping failing tests and builds, we studied the dimensions of missed failure observation to understand how many failures are not observed on time. For example, we measure the proportion of escaped failing builds among all failing builds in this dimension. Besides, since prioritization techniques can advance failure observation and selection approaches may delay it, we also studied the dimension of time to failure observation to understand the failure observations get changed after applying these techniques. For example, in these dimensions, we measure the positions shifted for failing tests within a build as the number of tests between every failing test's original observation position and its new position in one build. We have multiple interesting findings and observations in terms of these three dimensions. Due to the time limitation, I'm going to skip the graphs and jump straight to the main findings of this paper. Please read the paper to find more details. First of all, we observed that existing selection approaches have no preference on saving long-duration executions. In other words, they generally don't distinguish long-duration builds or tests with short-duration ones. So our first takeaway is that future selection approaches can be more targeted to save more long-duration executions for more cost saving. Second, we found that build preparation phase is time-consuming. This shows an opportunity for test granularity techniques to incentivize skipping full builds to be able to also skip the build preparation cost. We then find that none of our studied test selection techniques achieve this incentive. On the other hand, skipping tests can still save some cost. This incentive revealed the promise of hybrid build and test selection approaches. Build selection techniques have the strength of skipping many full builds, and test selection techniques have the strength of skipping builds partially. Future hybrid techniques could achieve both goals. Some of our selection approaches aim to save cost while trying to keep 100% of failure observations. To achieve this goal, they only skip builds with safe changes. For example, they only skip builds with only non-source code changes. Then we found that they can still achieve high savings. However, these techniques are not always safe. In other words, they still have some missed failure observation. Thus, we recommended future selection approaches to have better definition of saving costs safely in CI. Next, we made an observation that techniques training within projects saves more cost than the same technique training across projects. So we recommend selection approaches that require training process can achieve more cost saving by training within projects or be safer by training across projects. We also find that prioritization approaches can advance time to feedback, but provides no computational cost reduction. As a result, our next takeaway is to recommend future techniques to combine both selection and prioritization approaches in both granularities. Finally, we observed that higher savings achieved by selection approaches means more missed failure observation, which also means a longer delay, but is relatively low in terms of feedback time. This shows that there is a trade-off between cost saving and failure observation for selection approaches. So we recommend future research could design techniques to break this trade-off and also design better metrics to evaluate these approaches. To summarize, the main contribution of this work is we proposed the first comprehensive evaluation of CI improving techniques. And we included a collection of metrics in different dimensions. We also extended Travis torrent dataset and replicated different techniques under the same environment. Finally, this work provides evidence to design future techniques, such as allowing skip both full and partial builds. With this, I will be happy to answer your questions. Thank you.
Hi, everyone. Welcome to the Q&A for the paper entitled What Helped and What Did Not, an evaluation of the strategies to improve continuous integration. And we have the two authors, Xianghao Jin and Francesco Serva, with us. Any questions that you have, please post them in the chat. Thank you for your presentation. People take a few seconds to come up with some questions. If not, I've got a couple prepared myself. Okay, so maybe I can start. So Xianghao, thanks for the presentation. When I read your paper, I got so excited because you had this full-scale comparison, right? And I wondered if you actually answered the question, which one is best in something? Do you have that answer for us? Which approach?
Actually, I don't, since we compare them in different dimensions. And we point out different strategies, strengths, and weaknesses. But in particular dimension, different technique, one technique will be the best in the top list. For example, if we consider cost saving, maybe green technique or Hassan's technique performs better than the others. But if we consider the safety dimension, then the Abdulkarim's technique may be better. So they have their own strengths, and that's why we need to combine them to make them better.
Okay. I may have a follow-up question, but let's see from the audience. Na Meng is asking, do you have any thoughts on further improving the prediction accuracy of CI to skip?
Yes. Maybe one direct way following this research is to combine different techniques. For example, some techniques may be good at predicting those other techniques may be better at predicting more complex changes views. By combining them, we can make it more accurate. I mean, combine their strengths. Also, there are new papers coming out. The recent paper starting the build failure, what causes the build failures. They can use the signals like code smell or technical depth to connect these two factors to the build failures, build outcomes. Maybe we can use them to predict as well. Also, we maybe late in the future we can study the other more rules to understand which builds are going to be failed. Yeah. Thank you.
Sounds good. Edward is asking, can you tell us how many failing tests are missed? Aren't these tests executed eventually? And how much longer does the programmer have to wait before seeing the final results?
Based on our empirical study result, we can different techniques have different failing tests. The minimum of them could be like very close to 0% in median, and some techniques may be careless and they can skip like 50% of failing tests. This test can be executed eventually when their technique decided to totally run the test. Regarding of how much longer the programmer have to wait before seeing the final results, based on the evaluation, the execution time of those techniques are pretty short. I mean, like in seconds, but the build duration can be pretty long. Based on the other papers' statistics, like Google can wait for more than 30 minutes, and in our dataset, the median waiting result for 8 minutes. That's
okay, great. Zishi is asking, do you have any thoughts as to applying different techniques for different types of projects?
Yeah, I think so. Actually, different techniques are good at different projects. This is because different projects have their own culture or their own paces. Some projects prefer to build with very small changes, and other projects prefer to build with big changes. So for those projects with small changes or normally more safer changes, I mean, I think upgrade technique could be better because they are targeting at those, skipping those builds with those safe changes. But other projects may prefer like bigger changes, and in that case, maybe those techniques that trying to skip safe changes have no impact on that because they are not that changes are not that safe.
What about the types of systems? Sarah is asking, can you provide insights on the adequacy of the 10 techniques for systems with different levels of flakiness?
Yes, I think she means test flakinesses. In some of those papers, they consider the test flakinesses like the Mozilla paper. But for most of them, they didn't study they didn't cover the test flakiness in their papers. And I think it's a good direction to study in the future to consider the test flakinesses and to study how different techniques perform under this scenario.
Okay, we have a question from Sweden. Eric is asking, when prioritizing tests or builds, is there not a risk to prioritize on technical issues only? What about customer value? Did you consider any customer-related aspects in your analysis?
So I think I can take that one if because I think I know what he means. We did not look into that. We didn't have data for that, right? So it's really hard to to understand which kinds, how different changes impact the value of the software for the customers in different ways. Like that's a big research problem in itself, right? So we didn't look at that particular aspects, but I think that's a great point, that another completely different dimension on which to prioritize would be, let's just make sure that we have strong testing on the high value areas, and I think that in this paper we show that you could even use different techniques that have different trade-offs for different areas, because the very clear trade-offs that we saw is that those that are more conservative, that try to skip less to be more safe, also save fewer cost. So maybe in the areas that are not so mission critical, you could be saving more cost at the expense of maybe skipping more errors, but you're okay with that because that section is less important. Yeah,
I guess this question just raises the awareness of a bigger picture, not just technical issues. We may have time for one more question in the 1 minute left from Jasmine. Failing tests are often the most common cause for CI build failures. How do you safely select test phases to skip at the test granularity? And how do you mitigate test build flakiness?
Yes, in this paper, I replicate existing work instead of selecting test phases myself. To replicate existing work, I just replicate their algorithm. Some techniques do test selection by using formula of cost. Others use machine learning to predict which tests are going to fail. And for those, as I said, most of the techniques didn't consider the build flakiness and test flakiness. And that's my answer. Thanks. It's a good question.
Sounds good. Just a heads up, we have 20 seconds left and we're going to disappear from the room. Eric just made a follow-up comment that his question relates to the differences between continuous integration and deployment, where we could accept a problem for a short while if we can solve a need now. So it's a value of CI indeed.